Hey, hello everyone, and welcome to another session of the blockchain course. And today I'm going to talk about kind of a new topic. It's mostly about how we shouldn't give control to the miners, but we're going to go a little bit further and talk about randomness and how that works. I'm going to demonstrate these ideas using a very simple example contract. And the example that I'm going to use is a lottery. So let me just create a new file, and I'm going to call it lottery.sol. So let me just copy this. And let's say I have a contract that wants to do a lottery. So the idea here is that I want people to be able to buy tickets to this lottery, and I want to have a fixed price per ticket. So in this example, I'm going to have a price of exactly 1 Ether per ticket. That's quite a high price, but this is just for demonstration purposes. And yeah, we're going to see how we can do this. The main problem here is how to make sure we have a fair lottery where for every single person, the probability of winning the lottery is proportional to the number of tickets that they have bought. Okay, so let's start. The very first thing we have to do in a lottery is to sell tickets. So let's say I have a function that can be used to buy a ticket. So let's say I can call it buy ticket. It should be public because I want anyone to be able to call this and buy a ticket, and it should be payable because they have to pay the value of the ticket. Okay. And now what do I want to put in here? Well, of course, I have to first check that they're paying the right amount. So I would require that the amount that is paid when they buy this ticket is correct. So I would require that msg.value, which is the amount of money that was sent with this function call, is exactly 1 Ether. And then the next thing I have to do is that I should just make some notes that this particular person bought a ticket, right? So I can have an array or I can have a mapping. Doesn't really matter. We can use the same things that we had here. For example, we can have a mapping that for every address tells us how many tickets that address has bought, or we can just have an array of the addresses of every ticket, or we can have any other kind of mapping. Generally, we don't really use arrays in Solidity. We most often use mappings. So one thing I'm going to do here is that I'm going to have some integer that is going to give me the number of tickets that I have overall. And then I'm going to also have a mapping, but the opposite of this. So a mapping from unsigned integers to addresses. That basically tells me who the ticket owner is. So, ticket owner. Okay, so when I call this by ticket, it should first check that I'm paying the right amount of money. And if I'm paying the right amount of money, then it issues a new ticket, which is the same as saying increase the number of tickets, and then set the ticket owner for this new number to be the person who sent this message. So msg.sender, the person who called this function. Actually, it makes sense to put this before the previous one, so that if I have n tickets, they're numbered from 0 to n-1 now. Okay, so buying a ticket is not a big deal. The part that is actually interesting for us, and I will spend most of this session talking about, is how do we figure out the winner? So we should have another function that's I don't know what we can call it. Maybe we can call it a ruffle. And the idea is that this function, which is also public, should basically choose one of the tickets uniformly at random. And then the person who owns that ticket would be the winner of the whole lottery and will get paid. Right. Now, this is the main problem that we want to talk about today. How do we choose someone at random? Right? Or to be more specific, how do I choose one of the tickets at random? So I have n tickets. I want to make sure I choose one of them. So I'm going to first give you some non-solutions, and then I'll get to the actual solution. So one of the things that we've seen before is that in your contracts, you can actually access information about the blockchain. And you can access information both about the current block in the blockchain and the previous blocks and so on. So for example, you could read the block timestamp or the block hash or so on. And so if I just search this, there was actually, no, okay, this wasn't what I wanted. So it's called special variables. Yes, I can show this to you. So these are some of the special variables that you have access to. So for example, msg.value is something that we are using very often, and that basically tells us how much money was sent with the current function call. But there are a lot of other things. So in one of the previous attacks, we saw block.coinbase, which is the address of the miner who created this block. And we could use this to bribe the miner, right? And there is block.difficulty, which is like how hard it was to mine this block in terms of the proof of work. But there are a lot of other things that we can use here. And so one thing that we can use is called now. And now basically gives us the current block's timestamp. And we can also use block.timestamp for that. And we can also get the hash of a block. So if I get the current block's number, then I can get the current block's hash. So one of the most common mistakes that we see in smart contracts when they come to randomness is that they try to use the block timestamp or the block hash as the source of randomness. So let's do this here and then let's talk about what goes wrong. So let's say I use block.timestamp and I just say, okay, this is my random number. Okay, so my random number is just block.timestamp. Okay, and of course, I want my random number to be between 0 and n, between 0 and the number of tickets. So I will just take this modulo number of tickets. And at this point, this is not just a random number. This would be the winner of the whole contract, right? The whole lottery. So I will just have a winner. So I can say whenever someone calls ruffle, I will just set the winner like this. And well, let's say I have another function for redeeming the prize. So let's call this redeem. And this is public as well. And the idea is that whenever someone calls redeem, what do? We first require that the person who's calling this is actually the winner. So I want to require that the sender is equal to, well, winner was the number of the ticket. So I want it to be the ticket owner of the winning ticket. And then I would just send them the money, right? So I would just say, let's have someone who will get this, I will call it receiver, and this would be the person who sends this particular message, the person who called this function, and I have to, of course, make it payable. And then I just say receiver that transfer the amount of money that I have, and the amount of money that I have is number of tickets. Of course, it's in ether. Okay. But so the unit is actually Vey when we're doing this. So let me just Google this. How many Vey in an ether? Okay, I can just multiply it by this. Oh, a nice question in the chat is, why don't we just use this dot balance? And that makes sense, yeah. So I can just say pay the whole thing. Okay, I have to do address this balance. I can say just pay any money that I have to this person. And actually thinking about it, I don't have to even check this. I can just say the receiver is the ticket owner of the winning ticket. And then I can just send it. So it doesn't matter who calls this function, I will always send the money to the person who has actually won. Okay, nice. Now, there are a lot of problems with this contract right now, and you should never deploy a contract like this. But we're going to go over these problems one by one. Okay, the first problem I have here is that the ruffle function can be called many times. Right, so it is possible that I just keep calling the ruffle function until I win, if I'm one of the participants here. And generally, so one thing that I want you to have in mind is that when we are analyzing these smart contracts, we assume that everyone is an attacker. And we assume that everyone just wants to maximize their own payoff. So we have the game theoretic assumption that no one cares about anything other than making as much money as possible. So if your contract allows them to do something sketchy, people will do it. That's our assumption. And so here, for example, when I have this ruffle function and there is nothing in the contract that stops people from calling it several times, you'd better assume that people will call it several times. Okay. And actually, let me just say that this winner thing is public so that others can see it. And let's say the number of tickets is public. And let's say even this mapping is public. Okay. And by the way, again, when I say public, it just means that other contracts can access it, not that others can see it on the blockchain. Even if it's not public, everyone can see it on the blockchain, right? Okay. So I have these things here. And one problem was that the ruffle thing can be called several times. So maybe I can just have a flag that makes sure I cannot call ruffle more than once. So maybe I just have a Boolean. Let's have this one also public. I call it ruffle. Ruffle is called. And here I would require that it's not called. So require that the ruffle is not called before, and then set it to true. Okay, this is nice because now I'm sure that at least my ruffle function will be called exactly once. Okay. But another problem is that what if it's not called at all? So you see, I have this winner thing here. And as we talked about this before, the initial values are always well defined and they're always 0. So if the ruffle function is not called, the winner is by definition the owner of coin number 0, of ticket number 0. So I don't want that to be the case. So of course, in my redeem function, I have to also have a requirement that the ruffle is called. right? And this is a very common thing that you will see when you're writing smart contracts. You have to manage time and you have to make sure that your functions are being called in the order that you actually expect them to be called. Okay. But we still have a problem here with timing. And the problem is that suppose I call Ruffle and the winner is already chosen. Maybe someone else on the blockchain doesn't really know this and they're still calling buy tickets. So with this particular contract right now, it's possible that someone buys a ticket even after the winner is already chosen. And of course, they will not win. And here, because I'm transferring all of the balance to the person who's won, so basically what happens here is that if I'm the winner and I win it, I will just wait for a while. Maybe there is someone who calls buy ticket, and then I would call redeem and get all the money back. So I have to also do a requirement here to make sure that people don't buy tickets after the Ruffle is called. Okay. So again, this is very common. Usually when you design some protocol that has cryptography in it, so you've already done this in some of the homeworks. For example, you design the protocol for, let's say, rock, paper, scissors. And in that protocol, you used to have orders on the steps. And usually the way you would implement that as a smart contract is that you will have a function for each one of these steps. But then you have to make sure that these functions in the contract can only be called in the right order. So this is what I'm doing here with this Boolean. In this case, it's a very simple thing to check, but in general, it would be much more complicated. Now, okay. So what's the problem now? We solved the timing problem. And actually, in practice, maybe one other thing that we would do is that we wouldn't let this thing be as it is right now, because you see, it doesn't have a timing security vulnerability, but still anyone can call Ruffle at any time, right? And we don't really like that. So what I would much rather have is some sort of timer that says you can buy tickets before a particular block number, and then you can do the Ruffle only after that block number. So here I could just, instead of all of these things, I could say require block.number, block.number, right? Yes, block.number to be less than some number. So this means that I can buy tickets only before this block number. So let's say block number 1, 2, 3. And then here in the Ruffle, I could say require the block number to be more than 1, 2, 3, right? So this is another way of making sure the ordering is correct. I'm going to comment it out because I'm going to run this here in my virtual machine, and the block numbers don't make much sense here. But you get the idea. So I want to make sure that this function is called before this one, and maybe I don't want to just let people call this one at any time. So I can be more specific and say this function can be called before a particular time. But again, times are not something that we can depend on, because the timestamp is something that is set by the miner of the current block. So instead, what we would do is that we would talk about block numbers. And because a block appears at roughly predictable times, the block number is a good estimator of the current time. So it makes sense to say, I would be able to buy tickets for, let's say, the next 100 blocks. Or that I would be able to do Ruffle after that. Okay. So anyway, I'm going on too much of a tangent here. Let's go back here and see the problem. So as I just said, block.timestamp is something that the miner of the current block just chooses. And there are very little limitations on what the miner can put here. So the timestamp should, of course, make sense. For example, you cannot create a block that comes after another block and has a smaller timestamp. That doesn't make sense, right? So there are some checks in the protocol that doesn't allow you to just use any timestamp. And also, if you create a block that has a timestamp in the future, honest nodes would just ignore that block because it's obvious that you're playing with the timestamp, you're tampering with the timestamp. But other than that, there is really no way to tell if a miner is changing their block timestamp. So just think about what someone on the network can see. What they can see is a bunch of blocks that are coming one after the other, and they have solved proof of work. And so suppose that, for example, on a blockchain such as Bitcoin, where a new block comes every 10 minutes, let's say you've seen a block and the timestamp says that it was mined at 7 p.m. And then you expect to see another block roughly at 7:10, right? But you see a block, let's say at 7:09 or 7:10, and the timestamp says that it was mined at 7:05. That makes sense. Like there is no way you can tell that this wasn't actually a valid block, or that someone has, or that the miner has tampered with the timestamp, because maybe the miner just got lucky and solved the proof of work faster. Or maybe the miner was not lucky. Maybe it really took the miner 8-9 minutes to solve the proof of work, but then they claimed that they solved it in 5 minutes. So in Bitcoin, that's not a big deal anyway. And in Ethereum, the differences between block times are actually even smaller than that. But for this particular contract, that would be a problem, right? Because suppose that the miner also takes part in the lottery. And if that's the case, then the miner would just choose the timestamp in a way that maximizes the probability of winning for the miner himself, right? So if the miner owns one of the tickets, he can just choose the timestamp so that when we take the timestamp modulo the number of tickets, he wins. Actually, a more realistic attack would be that if this is, for example, a lottery that really has a lot of money, and it is because each ticket is now 1 Ether, as a miner, I can just buy a lot of tickets. And then if I'm sure that I'm going to mine the next block, I can just tamper with the timestamp so that one of my tickets wins. So that's another thing that the miner can do. But generally, this is another case of giving too much power to the miner. And as we talked about, I think 3 sessions ago already, let me see if I can find it. Okay, here we talked about the front-running attack, right? And there, the problem that we had was that we were giving too much power to the miner, in the sense that the order of the function calls mattered, and the miner was the one who could choose the ordering. So that was much more subtle, but here we have a much more direct problem. The miner, we know, can choose the timestamp, and we are just letting this thing happen. Okay? So not great. Another thing that we can do is that, okay, we say block.timestamp is chosen by the miner, so this is a terrible idea. Let me just write it here, terrible idea. Timestamp is chosen by the miner. But maybe we can use something that is not completely under the control of the miner. So what if we use block hash? And you see, I can take the block hash, and I just need to pass the block number to it. So let's say the winner is now based on the block hash of the current block, and of course, modulo number of tickets. Okay. What's happening? Oh, okay. So the block hash is not really an unsigned integer, we have to convert it. Does it work? Yeah. Okay. So I take the block hash of the current block, I turn it to an unsigned integer, and I use that as my random number. And I say just take it modulo the number of tickets, and that gives you the number of the winning tickets. So now this is arguably a bit better than the previous one, because in the previous one, the miner could just directly choose the timestamp. But now here we already have a hash, right? So it's not like the miner can just directly choose it. But this is still a terrible idea, because again, the miner has control over this block. The miner can choose what they include in the block and what they exclude. So the transactions in the block are under the control of the miner. And also the miner can mine this block using many different aliases. So one of the things that is definitely written into this block is the public key of the miner, right? And that's what we would call block.coinbase, right? So when the miner wants to mine a block, they at the very least write their own address into the block so that they can collect the gas fees and the transaction fees and the block reward, of course. So the miner has some control over what goes into the block. And if I'm a miner, I can just create many different identities, many different public keys and private keys. And then what I can do is that I can just form a block and take its hash. And if I saw that with that particular hash, I'm not winning the lottery, I will just discard this block, form another block where I'm using another one of my public keys as the Coinbase, and see if I will win this lottery in this new block. And I will just repeat this with as many times as I need until I get to a point where I'm actually the winner. So it's kind of like proof of work, right? But the difference is that the threshold is much lower. If I'm a miner and if I have one, let's say, if I own, let's say, a third of the tickets, or if I own 1/10 of the tickets, then I just need to do this 10 times on average. And I will eventually find a block that has the right hash and lets me win. So as you see, this is also awful because the miner can just form a block that has the right hash. Okay. So what else can we do? Well, another thing that we can use is block.difficulty. Now, this is a bit better because it's not really under the miner's control. So what is block.difficulty? It's basically like how difficult was it to mine the current block? So the difficulty of the hash cache puzzle, the difficulty of the proof of work puzzle that the miner solved. But the problem with this is that it's predictable. So anyone would know what the value is going to be. So this is also not such a great thing. And you can see that there are a lot of other variables here, and actually none of them are great ideas. Okay. So this kind of ruffling that depends on the miner is in general not something that I would suggest to you. I would much rather you do something completely different. Okay. So if we cannot rely on the blockchain and on the current block to give us the randomness, what can we do? Well, another thing that we can do is that we can just use the participants to create the randomness. So here's one simple idea. Let's say that each participant, when they buy a ticket, also give us some number. And then we will just somehow combine the numbers that the participants have given us and use that to generate our random number. Okay? So Here, when I'm buying a ticket, I say, okay, when you buy a ticket, you have to also give me some number, and let's give it a name. Let's call it this particular bias portion, for example. Okay, and I just keep track of this. So let's say we call this portions, and I just say portions number of tickets is equal to this portion. Okay. So the idea is very simple. Oh, sorry, this should be joined. I want these different people to just give me some numbers, and then I want to use these numbers to generate the final randomness. Now, again, I'm going to show you a lot of bad ideas before I actually get to a good idea. So here's one bad idea. We can just sum up all the portions that are given to us by the different people and take that modulo the number of tickets. Okay. So let's say I have a uint, which is sum of portions. And let's say that here I just say increase sum of portions by the current portion. And in the ruffle, I would just say the winner is sum of portions modulo number of tickets. Okay. Why is this not a good idea? Any ideas? Can you tell me in the chat why this is not a good idea? Yes, exactly. The last one, the last person who buys the ticket basically always wins. Because just look at it from the point of view of a participant. So let's say you are the nth person to take part, right? So you already know the sum of portions before you, and you know that the winner would be computed using this simple formula here. So as the nth person to buy a ticket, you will just choose your portion so that you win, right? And this actually happens repeatedly. So when the first person buys a ticket, the winner would be person number one. When the second person buys a ticket, the winner would be person number two, and so on. So generally what we're doing here is that we're saying the last person to be able to buy a ticket is the winner. And that's not great. So again, here the problem that we have is that it gives too much power to the last person. Okay, so let's remove this sum of portions idea. Generally, you see that we have to do some sort of game theoretic analysis. We have to constantly think who has power to decide what's happening here. It's not good if the miner has the power. Of course, it's not good if one of the participants has this kind of power. So I don't like this one either. How can we solve this? How can we make sure that people cannot predict who's going to win and choose their portion accordingly? So we've seen a problem like this before, actually, in the homeworks. And this was the problem that we had when we wanted to design a protocol for playing rock, paper, scissors, right? The problem was that we had two different people who were playing, and they had to kind of play at the same time, in the sense that they shouldn't be able to know what the other player has played when they're announcing their own play. And this is also kind of similar, right? So the problem that we had with just taking the sum of portions was that when the nth player was buying a ticket, he could know the sum of portions until that point. And then he could manipulate the rest of the results so that he wins. right? But what if the person doesn't know the sum of portions? So one thing we can do is that we can say, okay, instead of giving me your portion, you can just give me the hash of your portion. So we're going to do a commitment scheme. And here I will just have portion hashes. Okay. And what I do here is that I would just say add this hash to the list. Okay. So now whenever you buy a ticket, you don't just say what your portion is, you just say, here's the hash of my portion. And then of course, later on, you have to reveal your portion, right? So I will have another function. Maybe let's call it reveal portion. And it's also public. And the way it works is that you give a ticket number and you also give the portion itself. Now, at this point, it's really easier if I just say that I use this kind of timing instead of the original type. So let's say that I can buy tickets anytime, let's say, before block number 100. And then let's say I can reveal my portion at block number 100 to 200. Actually, 2 requires instead of 1. And let's say that I can call ruffle only after block number 200. And whatever, in case of redeem, I can just say this is a private function, and I can just say that ruffle calls redeem, right? So that I'm sure that redeem is called only once. So I'm just doing this to make sure that the timing is correct. So we first buy tickets, then we reveal our portions, then we do a ruffle, and finally we redeem. Okay. So what do I want to do in reveal portion? So I get the ticket number, actually we can write number, and I take the portion. So I have to check that this actually has the right hash. Okay, so I have to take the hash that I had. So the hash that I wanted it, so let's say declared hash is what? It's the portion hashes of this particular ticket number. And actual hash is, well, we have to hash the portion. It's given here. But okay, so we have to fix a hash function, and Solidity has a bunch of hash functions again. So I can just search for hash functions in Solidity. And you can see that, for example, it has SHA-256. Right, or it has a bunch of hashes here basically that you can use. Let's just use SHA-256. Or actually, well, okay, yeah, whatever. Let's use SHA-256. So let's say this is SHA-256 hash of the portion. We have to do some type conversions because I have to convert it to type bytes. And then the hash function also returns bytes, so I have to convert it back to uint. I'll add this later. It's always a headache. I don't like to do it right now. So you get the idea of what we're doing here. And then I would say just require the declared hash to be equal to the actual hash. And if it weren't equal, well, it's a require, so if it wasn't equal, I would just not accept the function call. And what next? Well, the next thing is that I just have to save this portion, right? So I would just say I have a mapping from unsigned integers to unsigned integers, and it's public, and it's called portions. And I would just say portions ticket number is now this portion that was actually declared. Okay, nice. And so when I'm doing the ruffle, I can just say, again, let's have a sum of portions that is initially 0, and then I just go over it from 0 to number of tickets. And I would just sum this up. Oh, okay, I have to use. Sorry. Sum of portions is I. And then I would, of course, say that the winner is just, as before, sum of portions modulo number of tickets. Okay. So we have a compiler error here because, again, for this particular hash function, I have to do type conversions, but don't worry about that for now. Just assume that it's working. So now, what's the problem now? So we don't have the problem that we had before, right? So if you are the last person to buy a ticket, or if you are the nth person, the only thing that you can see on the blockchain is the hash of the previous choices. So I don't know what the choices there were, what the portions themselves were. The only thing that I know is the hash of these portions. And so I cannot manipulate the result. I have to really choose my portion and my hash in a way that is totally agnostic to what others have chosen. And then when it's done like that, it really takes only one person to really choose it randomly, right? So again, we don't really have a proof of randomness here, because the only thing that is happening is that everyone is just giving out their portions and their portion hashes, of course, first. And then we're just summing up all the portions. This doesn't really prove to us that it's random. But actually, it takes only one honest participant, right? So if I have just one honest participant who actually generates their portion uniformly at random, then the final result would also be a number that is chosen uniformly at random. So that's kind of a good guarantee for randomness, because if you think about it, when we were talking, for example, about the Bitcoin protocol, the idea was that it works if more than half of the people, more than half of the computational power is honest, right? But here we're saying that it works and it's random, even if just one person is honest. If I have one person who buys a ticket and gives me a really random portion, then the final result would be random. Okay. But I still have a ton of problems here, and this is far from optimal. Like I can teach just this particular lottery contract for maybe 5 sessions if I want to go into it. But the first problem I have is that this ruffle thing here, it's using a lot of gas, right? So I have this for loop, and the for loop is basically going over every single one of my tickets. And that's generally not a problem if you're sure that the number of tickets is small. So if you had a limit here, if you said that I, for example, require that the number of tickets is at most, whatever, 10 or 9, so that I sell at most 10 tickets overall, then that wouldn't be much of a problem, right? Again, it wouldn't be nice to pay so much gas, but it wouldn't be a big problem. But if I don't have a limit on the number of tickets that I want to sell, Then here, what happens is that I have a 4 and it's going from 0 to the number of tickets. And of course, as we talked about this before, we have to pay gas for every single operation. So every time that this 4 runs, I have to pay a gas for this comparison. I have to pay a gas for increasing this I. I have to pay a gas for executing this line, right? So the amount of gas that I have to pay becomes unmanageable very soon. And at some point, it might not even be worth it for you to call this function, because maybe it uses so much gas that even if you're winning the lottery, it doesn't make sense. Of course, in this particular case, that's not going to happen because I set the value of the tickets to 1 Ether. So in practice, if you are the winner, you would call the ruffle function, because at the end of it, you get the redeem, and that gives you a lot of money. So you're fine with paying for this gas. But here's the thing. There is a limit on how much gas each block can use. And I can actually, again, Google that. So I can just search for block gas limits. Okay, so the block gas limit is 30 million gas. So what this means is that every block on the blockchain can use at most 30 million units of gas overall. So all the function calls, all the transactions in each block are limited to this much gas. Now, if the number of people who take part in my contract becomes really large, suppose that I have a really popular lottery and, for example, I don't know, 1 million people bought tickets in my lottery, then I will not have enough gas in one block to even call this function, right? So whenever I call this function, let's say it needs now more than 30 million units of gas because maybe I have a lot of participants, then the function call would fail. I will just get an out of gas error because I can pay at most 30 million gas in each block. So that's awful, because what it means is that this function can never be called in practice, right? Because only functions that use less than 30 million units of gas can possibly be put into a block. And so this function just doesn't fit into any block because of the amount of gas that it uses. So no one can call this function. And if no one can call this function, that means that the value cannot be redeemed. And so the money will just be locked into this contract, because as we talked about this before, when you pay money to a contract, you can get it back only if the code of the contract lets you do it. And in this case, the contract just doesn't let you do that. So this is an awful idea, and we have to write it in a better way. So let me just again say awful idea can cause out of gas errors and lock the money. Generally, we try really hard to write our contracts without any kind of loops. So we want to make sure that our contract does not have a for loop, our contract does not have a while loop. I mean, as you see here, there is nothing in the language that stops you from creating a for loop, but as soon as you write a for loop, you are opening Pandora's box. It's like you can get out of gas errors, you can get to a situation where some money gets locked, and also even if that doesn't happen, you have to pay a lot of gas for your loop. And usually it doesn't make sense to do that. So try to avoid loops as much as possible, and also try to avoid things that are equivalent to loops. So for example, don't write a recursive function, because a recursive function is just like a loop. So how would I do this now? Well, what I would do is that here I set the portions to be this, and I will just have the sum of portions like this. So I could just say I have my sum of portions here. And instead of having a loop in Ruffle, I just update my sum of portions in reveal. Okay. But now again, I have to be very careful about how I write this, because as I said before, if you have a vulnerability, people will exploit it. That should always be your assumption. So the problem with this reveal portion is that someone can reveal their portion several times, right? And in the way that it's written right now, it will be added to the sum several times. So that's also a terrible thing. And we have to just keep track of that, right? So for example, here, I would just require that the portion that I already know for this ticket number is not equal to the one that was just declared to me. Okay. Or alternatively, I can just have another mapping or a set where I keep track of which ticket numbers have already revealed their portion and which ticket numbers have not. And I just make sure that each portion is revealed once to avoid double revealing. Okay, double revelation. Now, as you see, there are like a lot of intricate things that you have to keep track of. Let me actually answer a question in the chat. So another, oh, this is a really nice question. The question is, what if the miner buys the first ticket and never allows other people to reveal their portions? Well, that's unlikely to work because we don't have a unique miner, right? So if you want to reveal your portion as someone who's taking part in this lottery, what you do is that you create a transaction that calls this function, right? And you just announce this transaction on the network. Now, one particular miner might not like this, but it's very unlikely that all of the miners are colluding with each other, right? So it's actually very much possible that, yeah, so if a particular miner doesn't like you and doesn't put your transaction into their block, the next miner would do, or maybe the one after that. So this goes back to the core Bitcoin assumption that we assumed more than half of the computational power is in the hands of honest miners. So if you have an honest miner and that miner successfully mines the next block, they will include your transaction, assuming that you paid enough gas and so on. But yeah, I wouldn't really consider this a vulnerability, because the way we would avoid this vulnerability is to just make sure that we are giving a lot of time here, so that no particular miner has a monopoly over mining the function calls. Okay. But actually, your question touched on a very important idea here. And the important idea is, what happens if I don't reveal? So let's say that I'm one of the participants. For example, I'm participant number 1. I have ticket number 1. And I wait for everyone to buy their tickets. Everyone has bought their tickets, and I have also bought my ticket, of course, and I've given out my portion hash. Now it's the time for revealing, and everyone's revealing their actual portions, and let's say they all reveal very fast, so I can see everyone's portions and I can see that I'm winning. So at this point, it doesn't make sense for me to reveal my portion. Right? So if everyone else has revealed their portion, and if I see that with the current value of sum of portions, I'm the one who's winning, then of course I would not reveal my own portion, because the portions get added only after they're successfully revealed. And if I successfully reveal my portion, I'm going to lose. But if I don't reveal it, I'm going to win. And again, this makes more sense if you think about a scenario where someone has bought a lot of tickets instead of just one. So suppose that I'm an attacker, and suppose that I have bought half of all the tickets, right? So it's very likely that when other people show their portions, I'm actually winning. Or I can even make it sure. So one thing I can do is this. Suppose that I have, for example, all the even numbered tickets. And I can do that because basically what I can do is that I can follow the blockchain, and every time someone buys a ticket, I will buy the next ticket, right? So I just make sure I have all the even tickets, assuming that I have a lot of money to buy them. Now, I will just have one of my tickets with a portion of 1. And then I would wait here for other people to reveal their portions. And I just look at sum of portions to see if it's odd or even. And I know that I will win if it's even. So if the sum of portions happens to be odd, I will reveal my portion, which was 1, and then sum of portions becomes even, and I win. If the sum of portions happens to be even from the very beginning, I just don't reveal, and again, I win. So as you see here, we have kind of like a 50% attack, which means that if I own all the, let's say, even number tickets, I can be sure 100% that I will win the lottery. And this is, again, assuming that everyone else is playing honestly and I'm the only one who's doing an attack. So this is not great. How can we fix this? You see, one way of fixing this that usually comes to mind at the very beginning is to just say, okay, instead of ruffling among everyone, what if we just do the ruffle among people who have revealed their portion? So if you don't reveal your portion, you lose the chance to win, right? So instead of like the number of tickets here, I will then have the number of successfully revealed portions, and I will take my winner modulo that. But that's not going to help, right? Because again, if you consider the case where I'm an attacker and I have 50% of all the tickets, it doesn't really matter for me if I don't reveal the portion for one of my tickets, and then I don't win on that particular ticket, as long as I win the whole lottery overall. And again, there is no authentication here. There is no way to say who actually owns each ticket. So for every ticket, we have an address. We have a public key of the owner, but we don't know who those addresses actually belong to. So anyone can create as many identities as they want. Anyone can buy as many tickets as they want. This is a very common scenario in the blockchain, on the blockchain. So yeah, we can't just say we exclude people who don't reveal their portions. Because if you just exclude people who didn't reveal their portions, that's not a good enough strategy, right? Someone is willing to lose one of their tickets in order to win. Well, another thing that we can do is that we can just cancel the lottery if this happens. So if at the end of this period that we had for revealing the portions, we check and see that there is at least one portion that is not revealed, we can say, okay, the whole lottery is canceled and we're going to redo the lottery. Okay. Would this solve the problem? If you think about it, this one is also not a great idea. Well, for several reasons. First of all, a problem that we have is that people actually paid gas for taking part in this lottery, right? So when you're calling this function for buying a ticket, and when you're calling this function for revealing your portion, you're paying some amount of gas. And so if the lottery just gets canceled because someone else was dishonest and didn't reveal their portion, then it's like penalizing everyone. Even if you give them a refund, you will give them a refund of 1 Ether, but their gas will not be refunded. So a way around this is to say, okay, I use the money that was paid to me for the tickets of dishonest people to refund the gas of honest participants. So one thing I can say is that if someone or a group of people did not reveal their portions, then I just take the 1 Ether that they had paid for each one of their tickets, and I would divide this among all the honest participants who actually did reveal their portions. And I would also cancel the lottery, and then we can go ahead and have another lottery. So this is a bit fairer, but it doesn't solve the problem entirely. Because again, think about what happens if you are a really rich person who owns all the even numbered tickets or half of the tickets. So what you can do is that you can still do the same attack as before, and you can say every time I check here to see if I'm winning. And if I'm winning the lottery, that's great. If I'm not winning the lottery, I don't reveal my portion, and that causes the lottery to be canceled. Right? And the penalty that I'm paying for causing this cancellation is basically just the value of 1 ticket. It's just 1 Ether, right? But my probability of winning the lottery was 50%. So now I'm getting another 50% chance in the next iteration of the lottery. And if I just have this situation continuing, basically each cancellation causes me to lose 1 Ether, but gives me a much better, a much worthier chance of winning in the next step. So suppose, for example, that I had 100 people taking part in this lottery. Suppose that I had sold 100 tickets. And let's say that the attacker holds 50 tickets. Okay? If the lottery is not canceled, and he sees that he's losing, he will lose 50 Ether. But the option that he has now is to say, okay, I don't reveal one of my portions, and by not revealing that one portion, the current lottery gets canceled, and in the next lottery, now I have a 49% chance of winning, assuming that he doesn't win 50, he doesn't buy 50 tickets again. So you see, at the very least, he's not losing his 50 units in the current lottery, and he's also getting a chance in the next lottery. So this is not good enough, right? How can we make it good enough? Well, we can increase the penalty. We can say that the penalty is much harsher. So, for example, one thing I can do is this. I can say, you take part in this lottery, and whenever you want to buy a ticket, you do 2 things. You pay 2 things. You buy the value of you pay the value of the ticket, which is 1 Ether in this case, and you will also pay a huge deposit. And this deposit should be more than the value of all tickets combined. Okay? And then I would say, if you don't reveal your portion in time, I will confiscate your deposit and pay it to everyone else in the contract. But even that is not great, right? Because if I say I confiscate and pay it to everyone else, you can just take part in this contract using many aliases and then get part of your own money back. So if you control a lot of the tickets, you can still manipulate and maybe get an advantage out of it. So instead, what I have to say is this. I say, when you buy a ticket, you pay the value of the ticket, which is 1 Ether, and you also pay a huge deposit. Now, if you fail to reveal your portion, I will use your ticket value to refund others for their gas that they used, but I will burn your deposits. I will not even pay it to the others. I will just burn it. And burning just means that the lottery, the contract doesn't pay it to anyone, right? Now, after all of these modifications, we get to a point where it really makes sense for everyone to reveal, and everyone is incentivized to definitely reveal in every case. But we had to add a lot of constraints. So one constraint that we had to add, for example, was that we have to now limit the number of tickets, because I want everyone to put down a deposit that is worth more than the value of all the tickets combined. So I have to know what is the maximum number of tickets that I'm willing to sell. Okay? So let's see how we can implement this. So I have the number of tickets, I have the tickets owners, the portion hashes, the portions, the winner. Okay, I'm not using ruffle is called anymore. And I have sum of portions. And okay, what else would I have? Well, as I said before, I will have some maximum number of tickets, right? So maximum number of tickets. And let's say it's 10 for now. So here, when someone is buying a ticket, I require that the number of tickets is strictly less than maximum number of tickets. Okay. And I can remove this one. And we are, of course, also checking the block number. This was so that we make sure everything is called in the right order. Now, what should message.value be? Well, it should be basically maximum number of tickets plus 1 times the ticket price. Okay, and let's actually have the ticket price out here. So I can say this is 1 Ether. So we are paying 1 ticket price for the ticket itself, and we are also paying maximum number of tickets times ticket price for the deposit that we want to be confiscated if we don't reveal our portion. And of course, we just record who sent this message, who owns this ticket. We record the portion hash that they gave us, and we increase the number of tickets. Okay, nice. Then we will have another function for revealing. Let's see if I have to change anything here. So the hash that we had declared in the previous step is what we have in the mapping. The actual hash is the SHA-256 of this portion. And we just require that the hashes match. We require that this is the first time that the portion is being revealed. And we record the portion and we record the sum of portions. This is fine. Okay. Again, we have a type problem here. So if you go over this, it tells you which types you have to use. Yeah, so you have to use bytes 32 and so what I can do is that I can say convert this to bytes and then convert the result to UNT. Work. Explicit type conversion not allowed. I don't know. I have to go and check like how the typecasting works in the in Solidity, but these are things that happen all the time. So I've had these problems with types every time I write a Solidity contract. Anyway, so let's focus on the things that we actually want to write. So we have this ruffle, but before the ruffle, I want to have a function for getting back your deposits. Okay, so maybe I'll call it refund deposit. And this is also public. And for this function, the only thing that I need is the ticket number. and I just check. I say, I check if the portions of the ticket number was actually given to me. So if portions for this particular ticket number is not 0, then I would pay out the money. And of course, I also have to have maybe since I'm using mappings, let's just use more mappings here. I just create a mapping called refunded to make sure that I don't refund someone more than once. So, and here I just require that refunded of ticket number is false. So I just require that I haven't refunded this particular ticket number before. And let's actually write this one as a require as well. I also require that I know the portion for this ticket number. Because if I don't know the portion for this ticket number, then that means that reveal portion was not successful. And if both of these things pass, I just set the refunded for this ticket number to be true. And I pay the ticket owner. So receiver would be the ticket owner of this particular ticket number. And I have to have address payable. And this should also be payable. And then I just say tickets number. Let's read this. I just say receiver.transfer. And of course, the amount of the deposit was maximum number of tickets times ticket price. I have to also be careful about reentrancy and so on, but we've seen that before. So we just make sure that this refund deposit is not reentrance, right? So make sure this function is not vulnerable to reentrancy. I'm not going to do it now. I've shown you how to do these things in previous sessions. So at this point, we're just refunding these deposits. So a question here is it better that we refund the deposit in reveal itself? You can do that as well. So one easy way is to just put this there, or you can remove the public and call it. It's your choice how you write your functions. Okay. But another thing that I want is that I want to have another function that people can call to tell me that someone has cheated. So here's the thing. We want to know if some cheating has happened. And we want to also know if, we want to also know who the cheater was, right? But I don't want to write a for loop because of the gas problem that I talked about before. So I don't want to say I have a function that at the end of the reveal portion part just goes over all the tickets and see if they have revealed or not, because that function is going to be super costly. It's going to have a for loop, and I don't want that. So instead, I can have a function here, and I can call this one reveal cheater. And the idea is that anyone can call this function, and it can just give me the cheater's number, right? And claim that this person has cheated. Okay, and this is public. Now, why do I do this? Because think about what's happening on the blockchain. So everyone is seeing who's revealing and who's not revealing. So everyone can just run a for loop on their own system locally and see which portions were actually revealed and which ones were not revealed. So each one of the participants can do that locally, and then they can call this function for me and tell me that the person with this particular number has cheated. Why is this better than I having a function in my contract that does this? Because when they run it locally, they don't have to pay gas for it. But if I run it in my contract, I have to pay gas. And I don't want to pay gas for a for loop because, well, we talked about it, right? I have to pay a lot of gas, and also I can get out of gas and a lot of bad things can happen. So instead, I will just have a function here that anyone can call and would give me the cheater. And yeah, so what I would do here is that I would just confiscate that particular cheater. So maybe I can just have another mapping from unsigned integer to bool, and this is public, and I call it isCheater. And when someone claims that someone else was cheater, I just say if the portion of this person who was claimed to be a cheater is 0, then set the isCheater to true. So isCheater, cheater number. Okay. And here I would, of course, also require that the person who is getting this refund is not a cheater. So require that not cheater. Oh, it was called isCheater. Sorry. Okay, so now only people who didn't cheat can get their refunds. Of course, I have to again think about the timing. So I said that in the first 100 blocks, you can call this one. In the next 100 blocks, you can call this one. Maybe we can give them another 100 blocks to call this one. And then we can get refunds only after block number 300. And we can also run the raffle only after block number 300. Okay. Another thing is that in practice, we usually don't just hard code the block numbers. Usually, I will have a constructor that writes down the number of the block in which this contract was actually put on the blockchain, the deployment block. And then I would here say that if the block number is less than the deployment block plus 100, instead of just saying that if it's less than 100. Okay. Yeah. So at this point, if we make sure that we have no reentrancy and if we make sure that we have no other bugs here, it seems like this is safe. Of course, I haven't implemented the part where we actually use the money from one person to refund the gas price for others. So that's also something that you can implement. I'm too lazy for that, honestly. So generally, the moral of the story here is that it takes a long time to write good smart contracts. But we have to also do one more thing. And the other thing that we have to do is that if it was revealed that someone has cheated, then we have to make sure that the raffle does not go through. And we have to make sure that everyone can also get a refund for their ticket. You see here, they're getting a refund for their deposits, but they're not getting a refund for their tickets. So I will also have another Boolean here. I call it cheater exists. And here, sorry, after I found this cheater, I will set that Boolean also to true. So cheater exists is true. And so in Ruffle, I would require that there is no cheater. So require not cheater exists. Okay. And then, of course, I can have another function here for another type of refund, or you could just merge the two together. Maybe if you make sure the timing is correct. So I can just say refund ticket price. And this is also public. And it takes a ticket number, right? And I have to check the time. So require that the block number is more than 300. And of course, I want to refund the ticket price only if this person is not a cheater. So it's very much like this refund deposit. So honestly, we could just make them into one function, but now I have two. So make sure that we have not refunded. Okay, I need another. I can have refunded and refunded ticket because I have two types of refunds now. It wants me to write it like this. Getting ugly, but you get the idea, and you can probably write it in a nicer way because I'm just writing it off the fly without actually thinking about how many variables I'm using. Okay, so I require that this person is not a cheater. They have revealed their portions. Actually, these two are now kind of the same thing. And if so, I will just pay them. And I have to pay them the ticket price. Hopefully now I don't have any more bugs. And this works. Okay. As I said, you can think about like how to minimize the number of functions. Maybe you can put the refund deposit into the reveal portion. Maybe you can just put the two refunds together. And of course, maybe you want to also implement some logic that says, okay, just confiscate the money off of all the cheaters and pay the money of the cheaters, divide it between others so that they can get back some money for their gas fees that they have paid. But as I said before, you shouldn't divide the deposit. You should only divide the ticket price of the cheaters between the others. And the deposit of the cheaters should definitely just be confiscated. And it should be banned. Okay, so now we have this contract that almost looks okay. I mean, we have to still do a lot of optimizations. Generally, when you write a smart contract, the first step is that you write your logic. The next step is that you make sure you don't have any of the common vulnerabilities. So I have to, for example, come here and add some extra logic to make sure I don't have reentrancy. I mean, well, actually, I'm using transfer. But anyway, so if I was transferring using a function call, I had to check that I don't have reentrancy. But then the next step is that you should generally go and try to minimize your gas footprint, right? So you want to pay as little gas as possible. And here we have like so many different mappings. And we have to pay for gas when we are saving something on the blockchain. And as I told you before, these are all stored on the blockchain. All the global variables will be stored on the blockchain. It's part of the state of the contract. Everyone has to reach consensus about this. So it's not a good idea to have so many variables and especially so many mappings. In practice, I would try to minimize these as much as possible. So some of these things are not really needed. So for example, the is cheater is not really needed because we can always find that information just looking at portions. And actually, the only thing that we need here for reveal cheater is to make sure that our contract figures out that a cheater exists, because the behavior is different. If a cheater does not exist, we will just do the ruffle, but if it does exist, we will refund the ticket price. And of course, I forgot to write that one. So we have to require that a cheater exists. Otherwise, we don't want to refund the ticket prices, of course. And as you see, there are like a lot of different constraints that you have to write. And as you just saw, it's very often the case that you can easily forget something. So you have to do a thorough vulnerability check on every single one of your functions. You have to really have an adversarial kind of thinking. So you have to think, if I'm an attacker and I see this contract, how can I attack it? So in this case, for example, the thing that you could do is that it doesn't, if I didn't have this line, you could just take part, and then you could also get a refund at the end if you didn't win, right? So you have to think about all the possibilities, and it is, of course, not so easy. But going back, I also said that we want to minimize the amount of gas that we use. So we want to minimize the number of global variables that we have, especially if those variables take a lot of storage, if they're mappings, for example. We also want to minimize the gas usage of our functions. So I was mostly focused on the ideas of how we are using cryptography, how we are using a commitment scheme here, what are the incentives, things like that. But I didn't really talk about optimizing my functions themselves, right? So there might be a way of writing, for example, this particular function that uses less gas than the way that I have written it right now. And generally, since gas is money, you want to do that. You want to minimize the amount of gas that you use. Another point that I just want to repeat one more time is that don't use loops unless you absolutely have to, because they use a ton of gas and they can also cause out of gas errors. I will probably talk about out of gas errors in one of the future sessions. So a lot of weird things can happen when you run out of gas. And there are actually a bunch of security vulnerabilities that can happen as a result of going out of gas. So again, the take-home point here is don't use loops and don't use recursion in your smart contracts. Honestly, you don't need them. Like, I've been writing smart contracts for several years now, and there was never a real-world use case where I wanted to implement a real-world financial contract, for example, a lottery or any other kind of contract, where I actually needed to have a for loop in there. So the language lets you do that, but that's an awful idea. Don't do it. What else? Yeah, and generally another thing that I would really recommend you to do whenever you write smart contracts is to have several other people read your smart contracts and try to attack them. There are actually companies right now that provide this kind of security checks as a service. So you can pay someone to do a security audit of your smart contract, and it's a good idea generally, especially if you're writing a contract that is handling a lot of money. You want to make sure that you get audits from 3 or 4 different places so that many different people actually look at it and try to figure out if there is a way to break it. And one final thing that I want to say is what happens if you're not careful enough. And what happens is something like the DAO hack. And I would really suggest that you read this blog post. So this is the URL. I'm putting it also in the chat. So in short, what happened was that there was this contract called the DAO, And it was a huge contract. It had tons of money. There was there was a vulnerability in the code of the contract. Actually, the vulnerability was due to reentrancy, and a hacker used that. And this happened back in 2016, I believe. Yeah. And they could basically steal something like $60 million from this contract because of the vulnerability. And you can read the details here. And as a result of this, actually, the Ethereum blockchain forked, because some of the miners said, this is clearly a hack. We're not going to allow this. We're going to just continue mining on the honest chain, and we're not letting the hacker take this money. But some of the other miners just said that code is law. This transaction is valid according to the Ethereum protocol. So if someone has made a valid transaction and that transaction is stealing $60 million from a contract, so what? That's the problem of the contract. So there was this division in the Ethereum community because of this particular hack. And of course, if you have a contract that has only a little bit of money, this kind of thing would not happen. No one cares if you get hacked for, let's say, $100,000. But if you get hacked and people lose $60 million, then at that point, the miners might come together and actually create a fork. And this is what happened in Ethereum. So the miners who said, we want to restore the stolen funds, became the mainstream Ethereum. So Ethereum right now is the chain that actually said, we're not going to allow this attacker to steal it. But the other people who actually just followed the protocol became what's now known as Ethereum Classic. And it's now a different cryptocurrency. And you can actually find that one. So this is Ethereum Classic, and generally the only difference that it had with Ethereum was that they didn't want to revert the DAO hack, but then over the years they have become even more different because some patches were applied to Ethereum and not to Ethereum Classic and vice versa. So now there are two completely different and separate cryptocurrencies. Okay, so that's all for this session. I'm going to stay a few more minutes and answer any questions that you might have. And the last point I want to say is that I'm really sorry for changing the time of this session. And this was because of a seminar that I have to chair. And I do my best to make sure it doesn't happen again. So my apologies for that.